Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
All right, let me just pull that one. Great. Welcome everyone to our first workshop in a series that will ultimately culminate in the Future Leaders in Quantum Hackathon. This hackathon will be hosted jointly by the International Telecommunications Union and the Student-Led Quantum Coalition as a part of the International Year of Quantum. Spanning 4 challenge tracks: science, education, art, and innovation. Each track is backed by a collaboration between industry partners and current student leaders in quantum. Over the next few weeks, we will be hosting a series of workshops to expose both newcomers and mavens to these diverse aspects of quantum, ensuring that you know which track you will like to pick when the hackathon begins on the week of May 19th. We will have more information soon, so keep an eye out on the quantumcoalition.io and the dedicated website we will be hosting soon. For our first workshop, we will be diving into an introduction of one of the most exciting areas of research today, quantum computing. Our host for this workshop is the esteemed Dr. Zlatko Minev, the technical lead and manager of Qiskit Leap Research and Qiskit Method, and as well as one of MIT's top 35 innovators under 30. Dr. Minev, the floor is yours.
Mihir, thank you so much for the wonderful introduction. And thank you guys for the invitation. It's absolutely my pleasure to be here with you. Let's get the slides up. So thank you to the organizers of this event. I'm very excited to get to share with you a little bit of the exciting journey of quantum computing and make this very practical and very much the edge of where things are today. So I couldn't be more excited to be here today. I hope so you are too. And why is today special? Because we're about to embark on an incredible journey, a quantum journey. And before we dive in, it is my delight that you should, as much as possible, interact. Even if this is a pre-recorded version, please use the chat. So today's goal will be to give you the tools, intuition, and curiosity to explore real-world quantum applications in quantum computing. Rather than cover a lot, our aim is to uncover at least a little bit for you, enough to make you even more curious. So let's dive in. In fact, raise your hand, so to speak, or put it in the chat. Even if this is pre-recorded, put it in the comment chat. Have you ever used a quantum computer before? You'll probably find that a fair number of you have or are about to. So here's what's coming up. First, we're going to look at the big picture. Why quantum computing in a nutshell? Why does it matter? How is it going? And where is the field? And what is the outlook for the next 5-10 years? Then we're going to take a peek at what a qubit really is in practice. How is it made? How does it relate to physics, to atoms? And finally, we're going to use that qubit to design a real quantum algorithm and run it on a real quantum machine today that you can use in the cloud and see what comes out and see what are both the opportunities and challenges and what to do about them. Sound good? All right, let's keep going. If you want to look at the slides, I think they'll be posted here through this course, or if you have other questions, you can try to find them also cross-posted on my little blog. So, part 1. What is the big picture today? How is it going for quantum computers? Well, the last 40 years has a lot packed into it, and we're not going to look at much of it other than the last 10. But let's first begin with the very early days of the 1980s And since then, I'll mostly focus on one platform called the superconducting qubit platform, which is what I'm familiar with. So let's take a quick time machine and write through history in just 60 seconds. So let's take a big step back and ask ourselves, why quantum computing at all? The motivation starts with one of the most fundamental challenges in physics and chemistry, simulating quantum systems themselves. Well, if the world is quantum, made out of atoms, everything is quantum, you could argue, nature itself. So let's go down to the lane in 1981, when Richard Feynman famously said, nature isn't classical, damn it. And if you were to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So what was Feynman getting at? Well, classical computers have fundamental limitations. They're inefficient at certain problems, in particular simulating quantum systems. Why? Because you could easily begin to say that the state of a quantum space is described in an exponentially large Hilbert space, 2 to the n. The vector in which the space lives is 2 to the n for n qubits, and that's exponentially large, and exponentials are tricky things to handle. Even for a modest system of 100 interacting qubits, if you want to capture all the detail in a generic system, storing the full quantum state on a classical computer would require, I believe, more memory than is available on Earth. Now, of course, there are a lot of tricks to get around this and make things more efficient, but Feynman's fundamental argument is that nature follows quantum laws. And then the best way to simulate them is by using a machine that also follows quantum laws and can inherently take advantage of this larger Hilbert space. So these foundational ideas led to what we now call quantum computation, leveraging superposition, entanglement, and interference to perform computations in ways that classical computers are unable to. Since then, we began to find algorithms such as factoring prime numbers, certain matrix linear algebra routines given certain conditions that can be performed more efficiently at a theory algorithmic complexity level than classical computers. Let's skip ahead the next 30 years and jump right into 2010s, which is roughly when I started running my first quantum algorithms, and give you a picture from then to now. At the time, this was the beginning of my PhD, this was an exercise in patience. What you're looking at here is a picture of the dilution fridge of my lab. This is a picture of me, and this is the dilution fridge in which we hoped there is a single qubit quantum bit working at the very bottom of this machine. Now you notice things are not going very well because there's a lot of gas essentially exploding out of the fridge. Things have gone poorly. You know, we were at the time we were lucky to have one superconducting qubit working sometimes, even for a few microseconds, before decoherence wiped out everything. And running a simple quantum operation, if you want, was like trying to do precise surgery while your tools evaporated in your hands. So the hardware was tricky. It's down at 15 millikelvin. And you see, most of our time was spent debugging. But we knew it was very exciting because we could see the progress. We could see how things could get better and better over time. So time has flown, 15 years, 2025, today, a 127 qubit quantum machine behind me here in this picture sits in the lobby cafeteria of the research building at the Cleveland Clinic, dutifully executing jobs, quantum jobs, almost all the time with very little debugging, continuous automatic calibrations, and hopefully, and as you can see, no more smoke coming out and shooting out of the machine. So these are operational, available via the cloud quantum machines that execute algorithms and are now beginning to push the boundaries of computation. We've moved from single unstable qubits 15 years ago to dozens of interconnected superconducting qubits with error mitigation, early error correction that begin to allow meaningful computations that begin to challenge classical computers. So this is a fundamental transition from an experimental curiosity in the lab to an emerging technology, industry, and computational paradigm. This is what a state-of-the-art quantum computing lab looks like, with each of these dilution refrigerators housing another set of quantum processors. And inside facilities like this, we're building quantum processors, designing cryogenic control systems, engineering error correction techniques, and having fun. The pace, of course, what you see is just the housing. The actual quantum hardware, the actual quantum chip, is very tiny and sits at the bottom of the fridge. And here's a bit of a progression from IBM Quantum on 27 qubits chips in 2019, all the way up to a couple years old now, this 433 qubit processor in 2022. So the pace of progress in quantum hardware is fast. Each generation is not just about more qubits, which you can evidently see here, but it's also about better qubits. Quality matters. Longer coherence times matter. Lower error rates matter. The smarter ways to mitigate noise and decoherence, the smarter ways to compile your algorithm matter. And if you zoom into one of these chips to give you a sense of the beauty and complexity of the technology, this is the IBM Osprey 433 qubit superconducting quantum processor. You will see that there are many layers to the chip, some with qubits, some with readout resonators, some with wiring, just wires actually are very complicated to interconnect everything. And this is a real interesting effort that is progressing. So what could I guess will happen in the next almost 10 years? Putting on a bit of my magic hat to try to predict the future, here's a vision of what 100,000 qubit quantum centric supercomputer would look like in 2033, where you have many fridges in little clusters interconnected with each other, realizing one large quantum machine or superintelligence, if you want, which would then encode a number of logical qubits. So there's a vision, there's a roadmap, there's a pathway. There are many different technologies using atoms and semiconductors and ions and so on. This is just one particular version of this vision. I find that very exciting, that we can look and peer into the future, and we have a nice, I think, optimistic perspective. But back to today, where are we today? And let's zoom in. How do we actually run a useful quantum computation with the hardware we have right now? So let's take an example of a quantum simulation going all the way back to Feynman. We want to simulate a two-dimensional spin chain lattice. Imagine some material. It's an out of equilibrium quantum dynamics that's generally very complicated. You see a bunch of spins on this honeycomb-looking lattice. And the goal is to track some magnetization, what the spins are doing. And these are quantum spins. This can be a tricky problem for classical computers, which can sometimes struggle with this due to the exponential state space growing, and also the way that the dynamics plays out. So could a quantum computer do better, or how do you even go about using it? So to run the simulation on a quantum processor, we have to take a few steps. First, this physical space picture you have on the left, we have to discretize, we have to understand its Hamiltonian, then discretize it, usually into what we call trotterization, or some other variational technique. So this is an algorithmic pre-processing step. We can then encode the spin state into a qubit, defining an efficient mapping. And finally, we translate all of that into the language of quantum computers, digital quantum computers, which are called quantum gates. So here on the right, you see a quantum circuit picture with qubit 0 through qubit 25. Each wire is a qubit, and you see a number of gates represented by these boxes for single qubit gates, and these joint boxes stretching like this. These are CZ control Z gates, doesn't really matter. The result is that you have some structure, you have a quantum circuit that can approximate and emulate and simulate the evolution of this physical quantum system. And that is a circuit that you can write in Python or your favorite language once mapped on a Jupyter notebook on your laptop. You can compile it, you can then submit it into a cloud API interface somewhere in the cloud and run it on a real quantum device in the lab, which then sends back data, streaming bits, zeros, and ones, classical data, the results of the measurements, all the way back to you. And this post-processing then allows you to reconstruct the physical observables like the particle magnetizations or spins. And this is where quantum computers can shine, trying to solve difficult problems. Not all problems, but some. So what does that mean for the state of where we are and where we want to get to? Well, this cartoon to me summarizes really nicely. This was an AI-generated cartoon where you get the idea that this dilution refrigerator housing the quantum unit is trying to outpace the classical supercomputers or classical computers we've seen over here trying to chase. Now, we're not quite at that stage yet. We're roughly somewhere around the corner of this, depending on who you ask. But the idea is to look for quantum advantage, which is when a quantum computer would outperform the best classical approach for a meaningful enough task in a metric that we care about. What does that actually mean or look like a little bit more tangibly? So the path to this next chapter of quantum can maybe be summarized crudely in the following picture, where on the x-axis, you can talk about the complexity of the circuit you want to execute. Let's say it's a quantum circuit. On the y-axis, you can talk about how expensive that is. How long does that computation take? And roughly, a picture for some problem of interest might look like this, where the classical methods here in gray scale very, very expensively. They're exponentially scaling and they scale very fast. So pretty soon, for a problem size not that large, you get into a regime where it takes you weeks, months, years, decades to solve that problem, even with the largest supercomputers. On the other hand, if you had a fully functioning, fault-tolerant quantum computer with all errors and noise being corrected, so we'll call that quantum error correction, perhaps there's an algorithm for that particular problem that is able to solve that problem initially at a much higher cost. It's usually going to take some overhead, but you see that the scaling then is not exponential in this case. So you get a huge quantum advantage here, or separation. Now, before we have fully quantum error corrected devices, as this is very difficult and tricky, but it's what the field is working on, and we'll get to in a second, we also have these quantum machines we're building today that aren't perfect. They have errors. We'll get to that in the third part of this lecture, but that doesn't mean that they're not useful. In fact, you can, as you know from any engineering practice, even if there's a noisy signal, you can always distill the signal from the noise if you're willing to average for longer, if you're willing to take more data. And in fact, that's the basic idea of quantum error mitigation, which is a kind of alternative or adjacent strategy to error correction, which we'll talk about in the third part of this lecture, which allows you to, at a cost, still ideally get a speed up over classical methods. So that's really where we want to get to next, to outperform classical methods before we get to full error correction. How far along this path are we? Where are we today? How do we think about the state of quantum computers? Well, the fundamental abstraction or unit in a digital quantum circuit is that of a digital quantum computer, is that of a quantum circuit, which again looks like this. We have 4 qubits, you have some gates, single qubit gates in boxes, and here C0 gates or control not 2 qubit gates on each pair of wires. In fact, this is a particular Trotter simulation. Doesn't really matter. So there are 2 axes, width and depth, or how many gates are there. So there's how many qubits you have and how many gates you have, or how deep you are. If you have 1 qubit, anybody can do that on their laptop. If you have 10 qubits, that's not very hard. If you have 100 qubits, that could be hard. However, qubits is not everything. You have to also think about the number of gates. because a bunch of qubits not talking to each other doesn't really do anything. It's not very interesting computationally. So what's also very important is how many interactions, how many gates are you able to do? And that's the x-axis. Because if you have 100 qubits, but you have one gate between them, that's trivial. Anybody can do that. So really the computational hardness and also where the field is headed and wants to go is up and to the right, where you both scale the number of qubits and you scale how many gates you can do. And that's when you can get into the regime that Feynman and Shor and others were talking about. So what I get very excited about is that in just the last 2 years, and it was almost an overnight shift, there was an explosion of experiments that started to push in a new regime that was previously completely inaccessible, which is to begin to do experiments at the 100 qubit plus level, which is well outside, if you want, of the lower green shaded region here as a kind of heuristic. Of course, this is highly heuristic. And now many of these experiments are beginning to push deeper and to the right into the regime with more and more gates towards harder and harder problems. And here I've taken a sampling of some of the very first and early experiments that begin to do this, with the largest ones at about 124 qubits and depth 60, number of 2-qubit layers, which is about 3,000 gates. What's exciting about the big picture of the community is that there's more and more examples like this. This is a sampling of many different experiments from the community. Some of these are run by students. Many are run within academic groups. To give you an example of one very close from our group, we used a quantum computer that looks like this, the one I showed you earlier. This is the actual layout where each qubit is a little circle. We can prepare the different qubits in some pattern, 0 or 1. So we start with the qubits in the 1 pattern, and then we can pretend that this is, not pretend, we can simulate this as an interacting spin system, a kind of material. And here's a movie taken from the quantum computer. This is real data. You can take a look at the paper, and we can study different regimes of matter, like a thermalizing regime, a pre-thermal many-body localized regime. So you can begin to study dynamics and computations that are not easy and not trivial to do in a classical simulation, and extract many quantities. This is just to give you a sampling of some of the things that begin to be possible. This is all data that came from the experiments. Now, we've taken a big picture look at what's possible, where some of the state of the art of the field, experiments, and the idea of quantum advantage. But let's spend a little bit of time on what actually is a qubit. Let's go back to the basics now that we've taken the big picture. Starting from the idea. Well, a qubit, in its basic idea, can be thought of as a system with two energy levels or two states. It's 0 or 1. However, those two states can be in any superposition. So in fact, the number of states that a qubit can have is infinite. It's a continuum on this sphere called the Bloch sphere that lives in the so-called space of Hilbert, or Hilbert space. This is what we mean when sometimes people say this qubit can be in 0 and 1 at the same time. That would be a state here halfway through on the sphere. But there's even more to it. You could ask, what's the phase? Is it 0 plus 1? Is it 0 minus 1? Is it 0 plus some complex number? And then you can move one level of abstraction lower, which is to say, what does that actually look like? How is it implemented inside the laboratory, inside of a lab fridge that looks like this? Or the Mona Lisa case, so this is this sort of more commercial version of the quantum fridge. How do we build these quantum bits? Well, let's look inside of this fridge that you've seen a picture of so many times and take out the shielding that's on the outside. That's just thermal shielding to protect you from the outside world, as quantum is sensitive. Inside of it is the golden chandelier. This is actually just piping and wiring, almost nothing else. This lives at negative 273.5 0.13 Celsius down at the very bottom of the last stage of the fridge. And actually, the quantum computer really lives only inside of here. And if you take out this can, it's a Matryoshka doll of cans, here's a picture of one of the early, I think, 16-qubit quantum chips from IBM, where you see a number of qubits patterned on this chip, which was, I think, silicon at the time, most likely, if you look at the papers. And you also see a bunch of squiggly wires, which represent readout resonators. You have to somehow read out the qubits and see what their state is. So you need extra components. And you see this repeating block of a little box where you have a so-called transmon qubit coupled to a resonator. And effectively, this is what all the qubits look like. And they're just stamped and repeated and sort of twisted and turned. And there's a lot of wiring. But the fundamental building block of this superconducting quantum computer is this picture. It's two metal pads connected by Josephson tunnel junction, which are then connected to this squiggly line, which represents a readout resonator. And when we talk about the Bloch sphere, the actual qubit, it lives here on the left. You see these two metal pads, the electrons sloshing back and forth, Cooper pairs to be more technically precise. This Bloch sphere represents their movement in a very, very low temperature state. We won't get into the details of it, but I'll just illustrate to you that you can talk about this at different levels of abstractions. You can talk about this as an electrical circuit. If you remember from your high school physics class or electronics class, there are capacitors, inductors. In fact, we could model this system as just capacitors and inductors. We can talk about some equations. But it gives you a flavor of the idea of how we start with the laptop, which is what you would interface with the quantum computer, how it submits a job to the laboratory, which then sends signals down into the chandelier, down these wires that go all the way to the bottom of this can, which itself then creates electrons flowing in this little metallic wires on this silicon chip, which themselves house electrical quantum circuits. Think of inductors and capacitors if you want. However, these are no loss inductors and capacitors. They have no dissipation. And also the inductors are nonlinear, but that doesn't really change the story so much, which themselves then are able to represent the Bloch sphere and the qubit. So the qubit is really the last layer of abstraction here. It's the most universal building block at an abstract level, but it's not a physical system in of itself. It is merely an abstraction that is mapped onto real physical systems like these superconducting electrical chips. And then what happens is you manipulate this sphere, which then causes currents and fluxes to oscillate in a particular way inside of this electrical circuits in a quantum way, which then sends signals back up the wires of the fridge, which sends signals into the lab electronics, which then send over TCP back some information over the cloud back to your laptop. For the more physics tuned in the audience, let's spend 5 minutes to just give you a bit more of an idea of the qubit from idea to reality and introduce some of these concepts, but back from a more historical picture. So we looked at the energy levels. Where do they come from in real life? Where does this Hilbert space originate from? Well, if you go back to the story of quantum physics, in fact, this is the origin of quantum physics itself that started with atoms. And it goes back, taking a big step back, all the way to the ensemble of atoms back in the early 20th century, end of the 19th century. People were able to put gases into little vials and begin to look at clouds of atoms. And this really was the state of the art of quantum physics until almost the 1980s, when scientists were finally able to isolate individual atoms. This is before artificial atoms like the ones we saw. with the qubits. So back in the day, people would take tubes of gas, put electricity through them, which would then generate light coming out of the gas. Now that light looked like some colors. Also, people would then put them through a lens. Scientists would put them through a lens, which could then be put through a narrow slit and a number of other optical devices, all the way down to a prism, which would separate out the colors. And you could then record the color pattern on a screen or some photographic plane. And in fact, what people observed, or scientists observed, is that different gases produce different color patterns or different spectra, such as violet, blue, green, red. And the different gases, such as hydrogen, helium, neon, sodium, mercury, etc., would produce distinct, discrete spectra. These experimental observations led scientists to understand that atoms have something new and more to them than what classical physics was used to. In fact, Bohr proposed in 1913 the idea of discrete energy levels, which you'll hear a lot about in quantum, to explain these atomic emission spectra. So he said maybe the atoms actually can only have energy in quantized units, hence quantum, where the energy can either be 0 or 1 or 2 or 3. It can only be in state 0, 1, 2, 3, and these states have some energies that are not evenly spaced. And this led to the idea that the colors we see on the left are simply differences in the energy levels. They're the atoms jumping from the 1 state to the 0 state and emitting a photon at the red color, or the atom jumping from the 2 state to the ground state and emitting a green color. Maybe that seems abstract, but you are extremely familiar with it anytime you've been out and seen fireworks or watched fireworks on TV. The colors you see in the night sky are precisely the discretization of energy that you see from atoms. Here you have yellow from sodium, you have lithium, copper, strontium, magnesium. These are the different colors. These are the spectra you see when fireworks explode. So it's a phenomenon that's not as unfamiliar as one might think. And in fact, these atomic energy spectra and transitions, one could then begin to connect with the way we thought of energy in classical world, where you could talk about what is the energy potential look like between an electron and a nucleus, which looks like this 1 over r potential. And instead of the electron being able to have any energy on the y-axis as a function of, say, the effective distance around the nucleus, the larger the orbit, if you want, of the electron around the nucleus, the higher the energy would typically be. However, what was realized is that the energy could not be anything. In Bohr's model of the atom, the energy had to come in discrete units, just like this. You could have an energy, the atom could have this energy, or that one in red, but never anything in the middle. That's the idea of quantization of energy. And in fact, the spectrum is special because you see the energy levels are not spaced equally. This represents a so-called anharmonic degree of freedom and spin. So when you shine a laser, or when you shine light at this atom, or when the atom emits, it does not emit at the same difference of energies, the same color, and it cannot respond, it cannot take energy at any unit. It has to take energy at essentially these discrete lumps of energy, hence the spectra. And that is how the very first qubits could begin to be implemented, because that means that if you shine light and you try to control the atom, you try to populate it or depopulate it, by choosing a particular color of light, you would only talk to these two energy levels and nothing else, because they're the only two that are allowed to be addressed by that particular frequency of the light, by that color of the light. So this anharmonic diagram allows, this energy level diagram allows for qubit-specific control and readout through this idea. Of course, there are always more than two levels. And that is still the way that quantum computing is done. Well, physics is done and quantum computing now is done with atoms, exactly through this idea. what we have seen so far is that atoms are not the only game in town. In fact, you can begin to build artificial atoms in the sense of their electromagnetic structure by implementing nonlinear circuits like this L and C. And that's in fact what these chips look like. They use capacitors and inductors on the right, which themselves have some energy diagram, which looks like this, where on the x-axis you might have the magnetic flux in the inductor, or maybe you have the charge in the capacitor. It doesn't really matter. Typically, that's a quadratic potential in a linear system, so the energy levels are spaced equally in red. However, when you couple this to the outside world, if you have equal energy spacings, you see that my pulse, which is at a fixed frequency, which is represented by the length of this arrow, can address any level. So what you have to do is you have to make the system nonlinear, and then that allows you to selectively couple only to the lowest two energy levels, for instance, and use that as your qubit system. So big picture, the idealization of a qubit is realized through an anharmonic oscillator, which you can selectively isolate the lowest two energy levels of. That's the 0 and 1 qubit levels. That can be realized through a physical model, which actually is corresponding to a physical system, metal, dielectrics, gunk on a chip. And the middle layer is called circuit quantum electrodynamics. You see the joke here is that there are two kinds of physicists, those who believe all of physics is spins and those who believe all of physics are oscillators. If you want to know more about the hardware side and all of this, here's a list, take a screenshot. I won't go through it. Here's another set of lecture series I've given that's a 6-hour, I believe 6 or 7 hours worth of content. So if you're curious at that, take a look. Instead, we're going to stop our hardware story there. And now we're going to turn to, if you want, the software side. We're going to go into how do we design and run a real quantum circuit in our final part of this lecture series, of this lecture. Let's start with a simple hello world experiment. Here you see the cartoon sketch of a quantum computer, one kept inside a superconducting fridge. Inside the fridge, we house a qubit that for now will look like this cartoonish sphere. And since we're going to abstract some of the detail, again, which is in these lectures, we will instead move completely above the level of the hardware now and look at the building blocks at an algorithmic level, which are the computational basis states, 0 and 1, written in Dirac notation, just to mention that they're quantum states, if you want vectors. We also have boxes which represent operations on these. Keep in mind that when I say X, that means bit flip. So X acted on 0 gives you 1, X acted on 1 gives you 0. Simple enough. And finally, we have measurements. In this case, we will measure in the Z basis, where measuring Z on the 0 state will give us +1, and measuring Z on the 1 state will give us -1. And X and Z correspond exactly to the X and Z directions in the block sphere picture. That's where the names X and Z come from. So here's a challenge for you. I'd like you to pause the video if you have to try to solve this. I would love for you to design a classifier quantum algorithm. Given the components we just saw, you don't need anything else. Classify or report if a classical positive integer d, such as 0, 1, 2, 3, 4, 5, 6, is even or odd. Pause the video and give it a shot. Okay, I hope you tried. Now, the simplest thing you can do, it's not extremely quantum, but is going to work nonetheless, and it will suffice for our purposes, is to flip the spin d times and then measure its polarization. So, for example, here's what depth 0 circuit looks like. We start in the ground state and we measure. This would correspond to D0. D1 circuit would say start in the ground state, flip the spin, measure. D2 would correspond to start in the ground state, flip the spin twice, measure, so and so on. Let's debug step by step through this circuit. So at the first step, all the circuits start in 0. At the next step, this first circuit is still in 0 and it's measured, and it will produce the value +1 down here at the bottom right. However, the rest of the circuits which have been flipped will now change from the state 0 to the state 1, like this. At the next level, yes, here's the measurement of the first level. We'll get +1. If we go to the next step and we do a measurement here of the state 1, according to our little rules, we will get the opposite value, -1. And so you see that if you step through the debugging steps, you will get +1, -1, +1, -1, etc. as a function of how many times you have applied the X gate, which is the input integer D. So this is a simplest version of a quantum algorithm where the data is actually in the circuit structure rather than the encoding, but for our purpose, it will work. Let's actually take this quantum circuit and let's run it on a real quantum computer. First, what should we expect? Well, we can write our circuit like this, where D is our input, and we will repeat the X gate D times and then measure. Here, I'll show you the plot of the output as a function of the input circuit depth D and what we measure to be the Z value. And as we saw in our debugging tool, all we're doing is flipping the spin back and forth, +1, -1, +1, -1, +1, -1, +1, -1. So you go back and forth. So ideally, that's what the data should look like in these red dots. And that's the spin flipping. Okay, now let's put it to a device and see what happens. Bum, 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 bum. Any predictions? Feel free to put them in the chat. And the big reveal is, here's the data. What happened? Oh no, it doesn't look anything like what we expected. How come it's decaying? It's oscillating? It's noisy? What happened? Is our quantum computer broken in every way possible simultaneously? Should we give up? Never. In fact, this is noise, and we have to, in a real quantum computer that is not fully error corrected, it's one that's run in the quantum cloud. And we have to remember this quote by the famous physicist Asher Perez, who said, "Quantum phenomena do not occur in a Hilbert space." That's an abstraction. They occur in the laboratory. In other words, real experiments do not occur in Hilbert space. They're inseparable from the imperfections and the features of the laboratory and the underlying quantum devices, which are unavoidably subject to noise. So, noise causes these errors as we see them. Noise is unavoidable. You can reduce it, you can decouple it, you can try to correct it, but you can never fully get away from it. Noise is here to stay, so we better understand it and understand how to deal with it. And that's a big part of what quantum computing today is about, and what running real experiments is also very much about. Let me just give you the elements of noise, and we'll leave it at that. Starting at the very beginning, you see that, first of all, even at the depth 0 circuit, already we are not getting what we expect. We're not getting the value 1, we get something slightly smaller. And that's because of what we like to call SPAM, state preparation and measurement errors. Preparing the ground state, not perfect. Measurement, not perfect. It has some errors. On top of that, there's a fundamental shot noise, which we'll get to in a second. Second, you see this general decay of the energy, and that's really incoherent noise. That's loss of energy, loss of information to the environment. Third, you see these oscillations. These are extremely characteristic of what we like to call coherent noise. Typically, that's a miscalibration of some gate, or it could be some coupling to a spurious system, or it could be some unwanted coupling between two qubits in the hardware design itself. And that's often what you see, is that they build out in these kind of oscillations. And finally, you see that even when the signal is totally gone, we don't get perfect results. And that is because there's a fundamental limit on the extraction of information from quantum computers. When you measure the quantum system, you get 1 or 0. You don't get the expectation value of the Z observable, of the Z projection of the Bloch sphere directly. No, not directly. So you have to measure many, many times, and this is projection noise because you have to sample many times. So instead of running our quantum simulation, our quantum algorithm in the cloud like this through this cloud service and have it in this perfect circuit, what happens once the circuit is run on the cloud is that errors shown here with these little red, uh, look at that, I can zoom, shown here with these little red arrows pile on and disrupt your calculation. And so you get something a little bit noisy. Now, what is the biggest challenge to quantum computers? Please type it in the chat. Now, you don't have to say that it's noise, even though I've just alluded to it, but I'd like to see what people think. In fact, I took this poll online on the trusted source of authority called social media, and people had all kinds of opinions from hardware development, coherence, material quality, hype, expectations, noise, algorithm development. But noise was the noisiest of them all, and is for me the biggest challenge to quantum computers today because errors corrupt experiments, as we just witnessed. They limit our computational reach. Noise is unavoidable, but that doesn't mean that this is the end of the story. In fact, we can learn how to deal with noise and deal with it. So that decaying picture that you saw, we can actually undo and fix that in our quantum devices today at a cost. But before telling you about that, let's think of what are generally the ways to deal with noise. Going back to 1995, Peter Shor famously introduced the idea of quantum error correction. The case when you monitor the system, you have a way to detect an error occurring, typically at the cost of a lot of extra qubits you would not otherwise need. And then you're able to detect that error and undo its effect. And that's error correction. That's where the field is going. There's a more recent way to begin to think about this, which is a much more recent paper, which is where you can monitor the system in real time. You can anticipate the occurrence of an error if you set things up in the right way by a telltale signal, and you can prevent it before it's ever manifested. So it's kind of pre-correction, pre-error occurrence. But that's too difficult to implement at scale at the moment. And ultimately, is the regime that you and I are left in for most of our work today is that we cannot monitor the system errors in real time. An error does occur, it goes undetected, but nonetheless, we can deal with it up to a point. And that's called error mitigation. So to contrast for you mitigation with correction, error mitigation is working with what you have. The benefits are that you will suppress errors on classical results. You're going to use this if you run any quantum algorithm today. The cost is that, well, there are actually no extra qubits or hardware resources needed. So no cost there. That's good. The classical cost means that just like with classical signal processing, if you have a signal with a lot of noise, you need to average for longer to extract the signal from the noise. And here you need to run many, many versions of your circuit typically, or sample much longer in order to undo it. So your runtime, your algorithmic time is higher. The limitation is that ultimately seems to have lower asymptotic scaling, meaning it's not the ultimate solution because for larger and larger circuits, you need to run for longer and longer. Quantum error correction is in a way the flip side of mitigation. They're not one or the other. In fact, you can mitigate on top of error correction. But error correction is the opposite limit, where you have a lot of quantum cost. You need many, many qubits to detect and notice errors. The classical cost can be a little high for decoding, but it's all post-processing. There's no extra necessarily runtime. The challenge is that it requires fault-tolerant operations and readout and just a lot of qubits and a lot of high-fidelity operations. And the gate errors have to be very low, so it's extremely difficult, but is what the field is beginning to achieve. Coming back to error mitigation, I would like to give you a very short high-level intuition for it without diving into any of the details, which you can find in other lectures or on my blog. I take inspiration by listening to music. I hope you do too. And I live in a noisy city, so I have to often put on my noise canceling headset. It's something like that with mitigation too. There's a lot of noise, but if you can learn the noise, if you can learn what the noise is on average, you can actually inject noise to cancel the noise. That's one way to think of a type of error mitigation. Just the way that noise canceling headsets actually inject more noise to cancel the noise, but in a clever way. And on average, you get no noise. So at a high level, one way to do mitigation is to learn the noise in an accurate and efficient and scalable way. That is not an easy thing to do, but there are ways to do it. You can then cancel it, and there's a cost. Noise canceling headsets are not cheap. There's a no lunch free theorem, and in this case, your cost is going to be in terms of the extra runtime required. At a high level, there are different mitigation techniques, like the one I just discussed called probabilistic error cancellation, which can be bias-free and in principle can almost perfectly mitigate and undo the noise, but at a very high cost. And there are more heuristic techniques like zero noise extrapolation, which are very fast, don't require as much sampling, but are not guaranteed to be as accurate in general. So there's a whole landscape, and we won't get into it here. I would just like you to be aware of that. So when you run an actual experiment today, when we run our quantum experiment on a quantum device now, we will run, instead of one circuit, many versions of that circuit in this mitigation framework, and each of them will have errors. But by post-processing the results of all those circuits and constructing them in the right way, we can actually obtain the right, or something close to the right values. Luckily, you don't really need to go deep into and understand all the details because most of this is automated for you, or there are packages that exist and work has been laid out by my colleagues and myself that you can use. So that brings us to the end of our talk and introduction to quantum computing and running a real quantum experiment. We have the theme of quantum advantage, which is the idea that a quantum computer will begin to outperform classical supercomputers in the best methods known on particular tasks, not every task, but some tasks, hopefully useful tasks. A key piece to that are going to be error mitigation and error correction. Error correction, as seen and shown here, is kind of longer term vision. Error mitigation is what you can do today. And as you begin to correct errors, they will not be perfect correction. So you will probably have to mitigate the logical qubits. You will do logical error mitigation concatenated with quantum error correction. And hopefully we will begin to see more experiments in this next regime and then further out and to the right, which is where the field is headed. So with that, allow me to end with my favorite quote from the great physicist Albert Einstein. I will let you read it. But the main thing is not to stop questioning, not to be curious, keep asking questions, go back through this video, post questions in the chat, keep the discussion going, and stay curious. So with that, it's been my absolute delight and pleasure. I hope this is just the beginning of your journey. Stay in touch. Say hello. Let me know you liked the lecture if you have any questions. And thank you so very much.
Thank you, Dr. Manav. That lecture was really insightful. I like kind of like how you took a full stack approach to exploring all the most important topics in quantum computing today.
Thank you, Mihir. Thank you. We covered a lot.
Yeah,
This was a very deep and narrow dive, and I hope you and the folks enjoyed it.
yeah, definitely. All right, I think that's all for today. We can close this. Yeah, thank you again, Dr. Manav. And yeah, I just have to emphasize, especially with quantum computing, there's no intuitive approach. You just have to keep studying, keep questioning, and go over these things multiple times. Yeah.
Yeah, and I will add that one of the quotes that keeps me going is that Henri Poincaré said that it is by logic that we prove, but by intuition that we discover. And intuition does guide a lot of this, but it will only get you the direction, right? And then you have the logic and the studying to actually prove it. You need both. But enjoy both. Thank you, Mihir.